In section 4.2, we begin to learn to classify chemical reactions, and we're going to learn to understand three different types of reactions: precipitation reactions, redox reactions, and acid-base reactions. And I'm going to make a video for each of these three types of reactions. So something we need to get out of the way fairly early on is that precipitation reactions are sometimes referred to as double replacement reactions. They're also sometimes referred to as double displacement reactions. And a term that's really kind of odd is they're sometimes referred to as metathesis reactions. So your book and myself will tend to always refer to these guys as precipitation reactions, but you may see this terminology elsewhere, and you should be aware of that. The first thing that we want to consider is what happens when a solute is dissolved in a solvent. In particular, what we want to be thinking about is what happens when an ionic compound is dissolved in water to form an aqueous solution. So what's going to happen is that there will be some attractive forces between the solvent molecules, in this case water, and the surface of our solid ionic compound. And what will happen is these water molecules will start tugging on the ions that are on the surface of our crystal, and if they can give enough of a tug, then they will be able to break the ion away from the surface, and the ionic compound will begin to dissolve. So if the forces of attraction between the solvent and the ion are greater than the forces of attraction of the ion to the crystal, then the substance will dissolve. And what are we going to be left with when that happens? We're going to be left with individual ions surrounded by water molecules in the solvent. So when an ionic compound dissolves in water, what happens is that the solid crystal becomes separated into individual cations and anions. And that's a really important idea. There are no neutral molecules present in an aqueous solution of an ionic compound. What there are instead are individual solvated positive ions and negative ions. And because we have these mobile charged particles, solutions of ionic substances that are dissolved in water are able to conduct electricity. Because they can conduct electricity, they're described as being electrolytes. So it's important to realize that electrical conductivity occurs because there are mobile, freely moving, electrically charged particles. And in this case, what our electrically charged particles are our individual anions and cations. So if I take a substance like pure water, the particles that are present are electrically neutral. They are molecules of H2O. So distilled water, pure water, will not conduct electricity. If I take a sample of a solid ionic compound, the positive and negative ions are not able to move. They're trapped in place within a crystal. So because there are no mobile electrically charged particles, solid sodium chloride or any solid ionic compound will not be able to conduct electricity. It won't function as an electrolyte. However, if I pour the salt into the distilled water and create an aqueous solution of sodium chloride, then I will have mobile, freely able to move sodium ions and mobile, freely able to move negative chloride ions. And sure enough, that solution will conduct electricity. So that's something to keep in mind. Aqueous solutions of ionic compounds are what we call electrolytes. They're able to conduct electricity. Why can they conduct electricity? Because present in the aqueous solution are charged cations and anions that are freely moving around and allow the electrical current to be conducted. Now, when we look at molecular compounds, many of those are soluble in water as well. Here's an example here. This is ethanol. Drinking alcohol, we normally drink it as a solution in water. Now, when ethanol or any other covalent compound of this, is dissolved in water, what we end up with is just a solvated neutral molecules. So solutions of covalent compounds don't dissociate into ions. They remain as intact neutral molecules, and these kinds of solutions are what we call non-electrolytes because they are unable to conduct electricity. There are no mobile electrically charged particles. Now, of course, there is a little bit of an exception here. I did say some covalent compounds. And why didn't I say all covalent compounds? Because if you recall, there are a class of covalent compounds called acids. So a good example of this is the substance hydrogen chloride. And when that is dissolved in water, it actually forms hydrogen ions and chloride ions. So if we were to take an acid and dissolve it in water, an acid is a covalent compound, then it actually does form ions, and we would expect that solution to be an electrolyte. It could conduct electricity. Now, some covalent compounds are what we call weak electrolytes. Only a few of their molecules dissociate in aqueous solution. And a good example of this is the class of compounds that are called carboxylic acids. I think there's an error in here. It should be an extra C in there. Carboxylic acids, not all of the molecules separate into ions. Only a few of them will separate into ions. And so what we end up with is a solution that's a kind of a poor conductor of electricity. And so these are often described as weak electrolytes. So if you take an acid, you dissolve it in water, and it doesn't form very many ions, you know that it is a weak acid where only a few of its molecules dissociate. So yeah, that's kind of an interesting idea. We can check for the presence of ions by seeing if a solution conducts electricity. Now, this is not anything new. You've probably noticed that some ionic compounds dissolve really well in water. These are the types of things that we see in the ocean. And what do we know sea salt is? Sea salt is sodium chloride, really soluble in water. Other ionic compounds are poorly soluble in water. A good example of this are phosphates. Now, the phosphate anion is very highly charged, so it sticks very strongly to sodium ions. It makes it kind of difficult to dissolve. So the ionic compounds that are not very soluble in water, they tend to be found on land, and then those that are very soluble in water tend to be found in the ocean. So we kind of know what are soluble and what are not soluble by looking at where these compounds are found. Now, I should say that for our purposes, we're going to consider that a compound is insoluble if its solubility is less than 10 to the minus 2 moles per liter in the given solvent. Okay, so a little bit of terminology about solutions that we haven't covered yet. A saturated solution is one that contains more than the maximum amount of solute. So basically what we do is we take our solvent and then you keep adding solute until some falls to the bottom. So you have solute that is undissolved on the bottom, and then you have your solution above it. And that solution has the maximum amount of solute in it, and that's called a saturated solution. And so generally what we'll do is we'll just take a given amount of solvent, put a ton of the solute in until we see that it's not dissolving anymore, it's just falling to the bottom, and then you filter that guy off, and the solution that you're left with has no floaty bits at no bits in the bottom, but it is what we call saturated. Now, if a solution doesn't have the maximum amount of solute, we'll take our solution. When you add a bit more, it will dissolve. So that's the check for whether a solution is saturated or not. If you add a little bit more and the solute dissolves, then it is not saturated. It's what we call unsaturated. Now, if you have a saturated solution and you add a little bit more solute to it, it'll fall to the bottom. All right, so that's the check as to whether something is saturated or not. Sometimes, if you get things just right, you can create what we call a supersaturated solution, which is really fun. And what you do here is you generally take like the hot solvent, which will dissolve more of the solute, and then you kind of like allow it to cool really slowly. And what you end up with is a solution that contains more of the solute than is theoretically possible. The only problem is that it's very unstable, and this supersaturated solution can only exist for a small amount of time, and then as soon as you disturb it, the excess solute begins to crystallize. So I'm going to try and play this video to illustrate this now. Let's see if this works. So what's happening here is we have a supersaturated solution of sodium acetate, and you can see putting the toothpick in there causes the excess solute to crystallize out. And the cool thing about this is it gets hot. So if you put a thermometer in there and kind of rub it on the bottom, there it goes, it begins to crystallize. She's touching it to kick it off a bit more, and the excess solute comes out, and it gets up to like over 50 degrees. So that's kind of cool, and there is all of the excess solute that crystallized out. You can also initiate this process by like pouring the liquid and letting it hit onto another surface. So we'll see that here it comes, and you can see the shock of the disturbance there causes the excess solute to precipitate out. This stuff is a little hard to prepare because it's an unstable state of the substance. Okay, so that's always kind of fun. You can look up, there's lots of YouTube videos about making supersaturated sodium acetate, and if you wanted to give it a go, it's pretty safe to do so. So some compounds that are, some ionic compounds we said tend to be or are soluble in water, and others are pretty consistently insoluble in water. You will need to have access to a list of solubility rules and know how to use that list of solubility rules. And I gave you a link in the module to one such list, but you got to know how to use it, and it takes a little bit of practice. Perhaps the first rule here that I've got is the most important one, and it says that ionic compounds containing group 1A cations and the ammonium ion tend to be soluble. Ionic compounds that contain the nitrate anion and the acetate anion also tend to be soluble, are always soluble in fact. Ionic compounds that contain the halide ions, these are ions of the group 7 elements, except those of silver, lead 2+, copper 1+, and mercury 2+, tend to be soluble. You'll see silver and lead cropping up as exceptions all the time. Sulfates tend to be soluble except for the larger members of group 2A, calcium, strontium, and barium, and then again our magic pair there, silver and lead. So what things tend to be insoluble? It's a slightly more complex list. Hydroxides tend to be soluble, except remember, group 1A is always going to be an exception, and then the larger members of group 2A, calcium, strontium, and barium. Carbonates tend to be insoluble, except those of group 1A and ammonia. Phosphates tend to be insoluble, except for the members of group 1A and ammonium. And then sulfides tend to be insoluble, except for, again, you guessed it, group 1A, ammonium, and then the larger members of group 2A. So these guys here, hydroxides, carbonates, phosphates, sulfides tend to be insoluble. And then we had a group 1A, ammonium, halides, or we can just go back to it. Group 1A, ammonium, nitrates, acetates, halides, and sulfates tend to be soluble. Okay. So this is the crux of things. When two solutions of ionic compounds are mixed, you might form a precipitate. The ions may be able to combine in order to form an insoluble compound. So if I have two solutions of ionic compounds, what I'm going to have present are two cations and two anions. And what I have to think about are what are the new combinations of cations and anions that could possibly form. So in this case, what I'm going to do is I'm going to combine solution 1, which is an aqueous solution of strontium chloride, with solution 2, which is an aqueous solution of sodium carbonate. Now, what we have to recognize is that the strontium chloride, because it's labeled as AQ, we know it's soluble. The solution is composed of strontium cations and chloride anions in a 1:2 ratio. The other solution is composed of sodium cations and carbonate anions in a 2:1 ratio. So now what I want to think about is what are the new combination of ions that could potentially form when these things are mixed. And what could happen is sodium ions could combine with chloride ions to form an insoluble compound, and strontium ions could combine with carbonate anions to form an insoluble compound. Now, how am I going to know if any insoluble compounds are going to form? How I'm going to know is by looking at my solubility rules. So when I look at the solubility rules, what I recognize is that when sodium ions combine with anything, because of my very first rule that group 1 compounds containing group 1A cations are always soluble, I know that sodium chloride will not form a precipitate. However, my solubility rule said that carbonates form insoluble ionic compounds, and strontium ion was not one of the exceptions. So this tells me that strontium carbonate will be precipitated as a solid. Now, once I identify that a pair of ions are going to form an insoluble precipitate, I do need to consider what the formula of that insoluble ionic compound will be. And in this case, I know that it will be strontium ions combining with carbonate anions in a 1:1 ratio, because these guys have equal and opposite charges. Now, if I had a different set of cation and anion, they may not be combining 1:1, and I'd have to take that into account. So let's have a look at this. I can write what is called the molecular equation for this reaction between the solution of strontium chloride and the solution of sodium carbonate. And in this form of the equation, I'm going to write all of the compounds in their undissociated forms, and all I'm going to do is indicate whether something is an aqueous solution or a solid using the little physical state labels at the end here. So let's go through and do this. What I know is that the strontium ions combine with the carbonate anion to form solid strontium carbonate. The sodium ions and the chloride ions remain in aqueous solution, and they're going to give me an aqueous solution of sodium chloride. Now I have to keep everything balanced, so I know that I'm going to require 2 moles of aqueous sodium chloride. Now this is a semi-realistic explanation of the situation, because we know that we don't actually have, aqueous strontium chloride molecules or aqueous sodium carbonate molecules or aqueous sodium chloride molecules. What we have instead are those ionic compounds are present as their individual component ions. That is, that those compounds dissociate into their individual ions because these are aqueous solutions. That should be AQ. Okay, so a more realistic situation would be to dissociate everything into the individual ions. So we'd end up with 1 mole of strontium ions, AQ, 2 moles of chloride ions, AQ, 2 moles of sodium ions, AQ, 1 mole of carbonate ions, AQ, and so forth. But notice here we don't dissociate the solid strontium carbonate because that's sitting at the bottom of our container as a crystalline material, and the ions are not present as individual ions. All right, so when we do this, we get an expression that is often referred to as the complete or total ionic equation. All right, sometimes it's called the overall ionic equation as well, but you kind of understand what they're talking about. It's the complete, the total, the overall ionic equation. Everything that is an ionic compound that is present as an aqueous solution is separated into its individual ions. But those things that are present as ionic compounds in the solid state, they're kept together to represent that this is a crystal where the ions are not able to freely move. So that's a second way of writing a precipitation reaction. Now, what you'll see here is that some of the ions in our overall ionic equation are in exactly the same form on both sides of the arrow. That it means that they're doing nothing. They're not reacting in any way at all. So what people will often do is, if the ions are in exactly the same form on both sides of the arrow, they'll cancel them. There we go. And then what we just are left with are the things that are actually reacting. And when we cancel out what these ions that are not changing form, we call them spectator ions, right? Because they're just kind of sitting there. What we're left with is this thing called the net ionic equation. It kind of focuses our attention only on those things that are interacting. Now, I'm going to give you a little bit of a hint as to how you can very, very quickly get the net ionic equation. So imagine I'm going to combine sodium sulfate, AQ, with barium chloride, AQ. So I think to myself, are there any possible things here that could, what are the new combinations when these two things are combined? Well, sodium ions could combine with chloride ions to form a solid. And I know that that's not going to happen. Sodium ions are group 1A ions and they never form a precipitate. But what about if barium ions combined with sulfate ions? And when I check my solubility rules, it says that sulfates are normally soluble except, and then barium is one of those possibilities. So I know that an insoluble precipitate of barium sulfate is going to form when these two things are combined. So what will be the formula of barium sulfate? Well, barium is in group 2A, so it has a 2+ charge, and sulfate has a 2- charge. So these guys are going to combine in a 1-to-1 ratio. So that's what's going to form. Okay, so now I've identified what's going to form. How can I very quickly write the net ionic equation? And this is the little trick. You identify what's going to form, and then that becomes your product. And then you write the ions that make up your product with the correct number of them, which is easy in this case, on the left-hand side of your arrow with AQ. So it's really quick to get the net ionic equation if you're asked for it. Identify what the product is and then work backwards and dissociate that into ions. The product will always be a solid. The individual ions that it's made from will always be AQ. The only thing to be aware of here is you've got to be, is this is a 1-to-1 case. You might need to change the ratio in order to get your correct formula. So if I did that here, I predicted strontium carbonate would form. I found the formula for strontium carbonate by looking at the charges on the anions. I go, okay, they're going to combine 1-to-1. So I would write this first, then the arrow, and then I would separate it out into the ions. So it's pretty simple to work backwards and get the net ionic equation. Now you have to be aware that when they, what form of the equation they're asking for. Are they asking for the total ionic or the overall ionic? Are they asking for the net ionic? Are they asking for the molecular form of the equation? You've got to be really careful. So here's another one. It says, predict if a precipitation reaction occurs when solutions of silver nitrate and iron 3 chloride are combined. So what's tricky about this? It's a word description. I have to know how to write the formulas for silver nitrate and for iron 3 chloride, or otherwise I'm going to be sunk. So I've got to know my chemical nomenclature, right? Or at the very least, I've got to be able to rapidly get to formulas by searching for that information. So I've got to be good at doing the naming, turning the names into formulas. So here's silver nitrate solution, going to be combined with iron 3 chloride. So silver nitrate will dissociate into silver 1 ions and nitrate anions, and then iron 3 chloride will dissociate into iron 3 plus ions and 3 chloride ions. So now we do the crossover. Nitrates are generally soluble, and iron 3 plus is not an exception. So that's not going to form a insoluble compound. Now consider the silver with the chloride. Halides are generally soluble except for silver, lead, and a few other examples. So this guy, the silver ions, are going to combine with the chloride ions. What are they going to form? Because they have equal and opposite charge, they're going to form silver chloride solid. So we're predicting that a precipitate of silver chloride will form. All right, we would predict a precipitate of silver chloride will form. It says if a reaction occurs, write the net ionic equation, and I kind of just accidentally did that. All right, so once you've got what the compound is, you can kind of just work back to the individual ions. He's doing it kind of in a more elaborate manner if you didn't want to do it the way that I did. I predicted that silver chloride would form. So I took my unbalanced equation and I had to balance it for the silver here in order to use up all of my chlorines that were present. So this expression here is the molecular equation, right? The molecular equation. That would be the balanced molecular equation. Now, if I separate everything that's present there, what do I get? I get the overall ionic, right? So that's what I've done here. I've separated out all of the AQ stuff. Note that I leave the solid stuff intact. Okay, never separate out the solids because that's present as a crystal, not as individual ions. So what do I do then? I look for things that have the same form on both sides of the arrow and I cancel them, all right? So boom, 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 boom. Once I do that, what I get is the net ionic. But what you can see in this case, it wasn't a smooth transition to what I actually want because I've got 3 of each of my ions of interest. 3 of these guys, 3 of these guys, and then 3 of the ionic compound itself. So what I'm going to do is divide through by that common multiple to give me this. Now you also saw that I can do the quick way AgCl. Solid was the solid that I predicted, and then I just work backwards and dissociate that into the individual ions and kind of do this in one step. What I've shown here is what you'd be wanting to do if you were asked to show all three different forms of the expression. Okay, you got to be aware that sometimes they're going to give you precipitation reaction problems that also involve concepts about stoichiometry, and I've mentioned this previously, concepts about naming. So this would be a good example of that. It says determine the mass of precipitate that forms when 25 mils of 0.1 mole per liter silver nitrate is combined with excess iron 3 chloride. So first of all, I have to be able to name silver nitrate. And then that's going to be combined with iron 3 chloride. So now I've got to figure out what the product is, and I've also got to balance the equation. So I know that the product here is going to be silver chloride, and then I'm also going to have FeNO3. I will need 3 of those, and then this is going to be AQ. So I'm trying to figure out the mass of the precipitate. This is the excess reactant, so that's not considered at all. And then this is going to be my limiting reactant, and what I know is that it's 0.1 molar, and I've got 25 mils of it. And my question is how many grams of that guy do I have? So I got to do some naming. I should also point out here there's 3 of those. I've got to get some balancing happening, which I just kind of caught myself on. And then, I've got to do the math at the end. So the first thing that I'm going to need to do here is get myself my balanced equation, right? So silver nitrate, that's AQ, with FeCl3, that's also AQ. What is it going to make? Well, I compare that. What happens when that combines with that? What happens when that combines with that? Nitrates are normally soluble, and Fe3+ is not an exception. And then chlorides are normally soluble, but silver is an exception. So silver is always +1, chloride is -1. They're going to combine 1 to 1. So I know that my solid is AgCl solid. And then what's going to happen with my Fe3+ there? Fe3+ is going to combine with my nitrate, and they're going to have to do crossover there. So that's going to be FeNO3, and that'll be AQ. We're almost there with our balanced equation. We've just got to take into account the fact that we've got 3 chlorides on the left, and we've only got the 1 on the right, so we're going to need 3 of those. We've also got 3 nitrates on the right and only the 1 on the left. So if we put a 3 there, everything balances. Okay, as mentioned previously, that was in excess. I had 25 mils of this guy, and it was 0.1 molar. And I'm trying to figure out how many grams of that. So a couple of things that I'm going to need here is I need to recognize that I got 25 mils of silver nitrate, AQ, and I get 0.1 mole of the substance silver nitrate, or I get 0.1 mole, I should say, of silver nitrate, the substance, for every 1 liter. But another way of writing 1 liter would be for every 1,000 milliliters. And then I know from my balanced equation that I get 3 mole of silver chloride for every 3 mole of silver nitrate. So it's a 1-to-1 ratio, or 3-to-3, so we're good there. So at this point, I could get moles of silver chloride, right? So 25 times 0.1 on 1,000. I don't need to do the times 3 on 3. So I know that I can generate 0.0025 moles of the substance. But what I need to know is the grams of it, because it said what mass, right? It didn't say how much. So sometimes it will just say how much, and you can give the SI unit for amount is the number of moles. In this case, it said the mass, so I'm going to need the grams. So I'm going to grab my periodic table. It's like 108 point something for silver and 35.45 for chlorine. So let's see what we get. Let's just get the exact numbers. Silver is 107.87, and then chlorine is 35.45. So that means my molar mass for silver chloride, 107.87 plus 35.45, we go 143.32 grams per mole. So let's give this a go now. Just calculate the molar mass of silver chloride. We have 0.0025 moles of silver chloride, and then we just got to multiply that, recognizing that we get 143.32 grams for every 1 mole of silver chloride. And there we are. And we ended up with, we want two significant figures here, 0.36 grams. Okay, so relatively complex problem there. It's got a little bit of naming in there. It's got a little bit of molarity stuff in there. Got a little bit of balancing equations. And then finally, you have to do the stoichiometry and calculation. Okay, so that concludes the section on precipitation reactions. There'll be another 2 videos describing the other 2 types of reaction classes we're going to be working through in section 4.2. So, good luck with everything.